Welcome back to unit number 3 on magnetic fields. In this video lecture, we will see what a magnetic field is and how it will be generated. I hope that by the end of this video lecture, you will be able to describe the concept of magnetic fields and also the concept of magnetic force. As we all know that we might have studied in our intermediate or our class 10 that there will be magnets. Normally, magnets will be having North Pole and South Pole, and these magnets are generally considered as bar magnets, right? This is the general representation of a magnet in our higher education, in our secondary education. And we might have also seen that there will be lines of force which will be coming out from North Pole, and the lines of force will be coming to this South Pole, isn't it? So normally if there is a single bar magnet, we will be drawing in this fashion, isn't it? And we might have seen that these are called as magnetic lines of force. We might have done these experiments with iron fillings on this bar magnets, isn't it? And these are termed as magnetic flux, represented by the symbol phi and measured in Webers. Right, this is what we have learned in our secondary education or class 10. But this magnetic field, which we have to remember, is that it is a vector field and it is having a direction. It always moves from North Pole to South Pole. It's not only that the natural magnets, we do have electromagnets also, which you might have studied, right? An electromagnet is just like a coil. If you allow a current to pass through it, then automatically it develops a magnetic field around it. It just behaves like a magnet. The coil is behaving like a magnet. And this, if you remove the current, then automatically it will just be a wire. But if you allow the current to pass through it, it will behave like a magnet. So that's why these are called as electromagnets. Just like the natural magnets, electromagnets also they develop a magnetic field. And that's why in this particular slide I have mentioned a magnetic field is a vector field in the neighborhood of a magnet, a natural magnet, or an electric current which is giving out electromagnet, or changing electric fields in which magnetic forces are observed. It's not that a natural magnet or an electromagnet, even if there is an electric field and it is continuously varying, it also develops a magnetic fields. And normally magnetic fields are produced by moving electric charges, what we call it as currents. So any currents can develop a magnetic fields. And intrinsic magnetic moments of elementary particles associated with fundamental quantum property known as spin. This concept we will omit it because this comes under quantum physics. We will eliminate this one. We will focus only on this magnetic field is produced by moving charges, which means any current is responsible for developing a magnetic field. And we have already seen that if there is a current, which is nothing but there is a movement of charges. If charges are there, whether they are moving or stationary, it develops an electric field. And if they are moving, they can develop magnetic field also. So charges, whether stationary or moving, they can develop electric fields. And if they are moving, they can also develop magnetic fields. So which means that both electric fields and magnetic fields are both interrelated. And these are components of electromagnetic forces, which is one of the 4 fundamental forces of the nature. Now, as already mentioned, magnetic flux is nothing but magnetic field lines, which are a visual tool to represent the magnetic fields, and they are often measured in Webers. And one particular quantity which is generally often used to measure magnetic flux is magnetic flux density, represented by the symbol B, and is defined as magnetic flux per unit area. So its units are Weber per meter square, or we can represent as Tesla. In some textbooks, we will use another unit called as a Gauss, which is a smaller value of Tesla. So 1 Tesla is somewhere around 10,000 Gauss. Okay. Now, another term which is used to represent magnetic field is magnetic field intensity, often referred with the symbol H. It is defined as the ratio of magnetomotive force which is needed to create a flux density within a particular material per unit length. Okay. And its units are ampere per meter. Try to remember, B has Tesla or Weber per meter square. It is flux per unit area, whereas this one is magnetomotive force to create certain flux density within a particular material per unit length. So this is H. Its units are ampere per meter. And the relation between these B and H, we have seen these two similar terms, D and E, right? In electric fields, the relation between them was D is equal to epsilon E. Similar to this, here also we do have. So B is equal to mu into H, where mu is called as permeability. This is permittivity. In electric fields, we call this term as permittivity. In here, we call it as permeability, represented by mu. Just like here, right? Absolute permittivity is nothing but relative permittivity into permittivity of free space. Here also, we will be having. Okay. Now, a quick review. The sources of magnetic fields. This is a bar magnet. I have already shown you. This is a solenoid, which I have already mentioned, which is generally termed as an electromagnet. And this is a current in wire, a normal wire, electric wire also. If it is carrying current, it can develop magnetic fields. And the direction of magnetic field is given by thumb rule, that we will see. And this is a loop of wire. Now it is also capable of developing magnetic field. And in this figure, you can see the directions of magnetic field, how they are developed. And the Earth is also a very big magnet which is developing magnetic fields. So the key point is electric charges at rest produce electric fields, while the charges in motion can develop magnetic fields. So any charge in motion develops both electric field and magnetic fields. Okay. Now we'll close this session with a quick introduction to magnetic force. So when a charge, let us suppose if there is a magnetic fields which is in this direction, magnetic fields. Now if I take a charge and I move it in this direction with a velocity of v, and this is the direction of v. So the force which is experienced by this charge is given by F bar is equal to QV bar into V bar. Try to remember this particular expression. We will see on this one in next video lecture. Okay. Do remember this is force experienced by the charge which is moving at a velocity of v in magnetic field of density d. Do remember these two are vectors. This is also a vector, and this is a cross product between them. Okay. So with this, I will close this session, and we will discuss more in the classroom session. Thank you.